So we're going to be looking at dilations again in a different capacity as it relates to determining if two shapes are similar or not. So before we get too far, we're actually going to manually calculate and prove if something is similar just by measuring all the parts of two different triangles. So we got 3 angles and 3 sides we're going to calculate. You can remember that we have 2 parts. One's called the pre-image, which is A, B, C, and then the image, which is denoted with these apostrophe-looking things. So you know that's called the image or the after. Like this is the before, this is the after. So we pronounce those as A prime, B prime, and C prime. So we're going to find all those measurements of the 3 sides, and then we're also going to use the protractor to calculate all 3 angles. So we can see the properties of 2 triangles that are similar to one another. So for the sides, let's do those first. We're going to use the centimeter part of the protractor, which is on the inside right here. And calculate, I'm going to start off with, let's see here, AB. Let's go in order. And we're going to round just a little bit on this one and call this to be 6 centimeters. And then do the same thing for AB prime. Right. And this one comes out to 3. So the same rules follow. We always want to look at corresponding parts in pairs. So that comes out to be 3. And then repeat the same process for the other 4 sides. So we can calculate let's see here, what's next? BC, so calculate BC. Looks like it's 3. And then BC prime, like this is 1.5. There we go. And then continue, do AC. Here at the bottom, looks like that is 4. And looks like AC prime is 2. Okay. Good. So this would be the way to prove something is similar by exhaustion. Basically, you measure all 6 sides, see what they are, right, and then see if there's the same relationship between each pair of numbers. Okay. So let's look at that first. Let's skip down to, and let's just look at the ratio between these 2 numbers. You could probably already see what the pattern is, but this is how you're going to prove mathematically if something is similar or not, right? And that is that they should come out to be the same ratio. So AB on top, AB prime on top, which is right here, which is 3. Okay. And then AB, the original, the pre-image on the bottom, and that reduces to 1/2. Okay. And then repeat the same process. We have AC prime. right here, which is 2. And then we got AC, which is 4. So that also reduces to 1/2. And going on to the last, BC prime, 1.5. And BC, which is 3. And that also reduces to 1/2. So that is the definition of similarity, where the whatever polygon you're working with, doesn't have to be a triangle. They have the same shape, but the size of them are different. In this case, it's going to be a reduction, okay, of size. Okay, and it's by exactly 1/2. So mathematically, you could say that this triangle is half the size of this triangle by length, okay? Exactly 1/2. Okay. Now, what relationship will the angles have, though? In order for them to be the same shape, what would the angles have to be? Would those be half as well? So let's go ahead and measure those. Let's measure angle A on an angle A prime. On each of these. And see what those come out to. Now, you might remember when we're using this, you want to put the dot right here on the vertice, so on A, and then there's a line. See, there's this line right here, that black line. You want to line it up with the base of the triangle or side. Right. Then we want to use these numbers over here to measure it. Now, it does look like this triangle is not big enough for this protractor. So you might recall that when that happened, we went over here and extended it so we can measure it accurately. You want to go like this and extend this line as far as it will go, and go back and measure it again, and we should be able to see it this time. There we go. That looks like right about there. Now, this is an acute angle, right? So we're using the smaller numbers right here. We're not going to use, this is definitely not 150, 160 degrees. That would be almost a straight line. So it's a very small angle, acute angle, so we want to use these numbers. So it's between 20 and 30. Now, if you follow it up, you can see the more precise measurements here, these tick marks. So here's 20 and 30, which means this big one right here is in the middle of 20 and 30, which is 25. And our line actually is one bigger, or one closer to 30. So that makes this 26 degrees. So angle A comes out to be 26 degrees. And then repeat the same process with A prime. Got to extend it and then measure it. And any predictions what will happen? Yeah, so come up with a prediction and then let's see if it's true. And line that up perfectly. And it may not be, precisely exactly, but when I do mine here, it does come out pretty close to 26 as well. So that's the other side of similarity. When we're talking about similarity, we're talking about same shape, different size. And shape turns out to be angles. Same shape means same angles. Different size means, well, we have different measurements on the size, but they do have the same scale factor. So let's just verify this all the way. Let's do a measure of angle B. So we might have to extend this one down. And this one down, doing both. Okay, pen on the vertex, line up your black line. Okay, right about there. And it's between 30 and 40, so it's going to be 30-something degrees. And you can see here's 35 right in the middle, and it looks like it's 2 more over from there, so 36, 37 degrees, approximately. And we move it over here, and we'll get, hopefully, approximately the same thing. And it does look like that. Here's 35, 36, 37. That's about right. There we go. For our measure of angle C, since we already do have these, we could just subtract from 180, and I think we'll have to, because if we go to here and try to measure of angle C right here, we'd have to extend this line would have to go off the paper, so I think we'll have to do that. Or we could go like this way and extend this line. I guess we can get it that way as well. But I think just for time's sake, we'll just calculate it. So we can take this for these two, just take 180 degrees, right, and subtract 26, and subtract 37, and that will give us those two. So 37 and 26, subtract both of those. And we'll get 117 degrees for each one of those. So those are the two conditions that must be true. Angles must be the same, whether we're using a protractor or we're solving it with algebra. And the sides need to have this same scale factor. Okay, so for it to be similar, these blue scale factors, we call them, must be the same. Okay, there we go, for them to be similar. So if they're not the same, if we don't have the same scale factor, or if the angles are different, then it's not similar. Okay, so that's going to be our goal. Now, technically, we do have to show that every single ratio does come out the same. We're not going to be going to go all the way and do the same thing 3 times for a triangle or 5 times for a pentagon. We're just going to assume that they are, unless there's some evidence that says the contrary. Okay, so formally, right, we have dilations, right, is something that a transformation that can change the size of a polygon but leaves the shape unchanged. Okay. When we're talking about shape, we're talking about the angles. And we're talking about size, we're talking about side length. Okay. So that's just a nice summary of what we just did above. Side lengths were different, but the shape, the angles were the same. Okay. So all of these, angle A and A prime must be congruent. Angle B and angle B prime must be congruent. And angle C and C prime must be congruent. However, the side lengths will have some ratio that must be the same for each pair, each corresponding side. Okay, so this number, we call this the scale factor, okay, which is the ratio of the corresponding sides in the image and pre-image. Okay, and if we have like we had up front, it got smaller. That's called a reduction. Okay. Oh, by the way, for scale factor, we usually call that K. kind of like for slope, we use like m, just so if you say k equals something mathematically, it's assumed we're talking about a scale factor, so we use k. So if it's getting smaller like we did above, you notice how the k value is smaller, right? So the k value is less than 1. One factor, if you remember, would be unchanged. So an actual scale factor of 1 means the shape doesn't change. Anything less than 1 means it's getting smaller. Technically, between 0 and 1, it can't be a negative, but between 0 and 1 it would be a smaller, kind of like 50%, makes it smaller. Okay. Then we have the enlargement, which when the shape gets bigger, and that would be the k value is bigger than 1, or bigger than 100%. So below, we're just going to do 3 problems and just determine if it is a dilation and give the scale factor. So for the first 2, we're going to assume that it is a dilation, and just by looking at them, you can see these shapes definitely are the same shape. The angles do look like they're the same. Okay. So what we're going to do is just calculate what this ratio is up here. So just notice how this is the image divided by the pre-image, okay, or the after divided by the before, or the ending over the starting. You want to make sure you get those correct from the very beginning. If we just accidentally put 6/3 instead of 3/6, it means the exact opposite. Instead of half as big, we're saying it's twice as big. So kind of like slope and rise over run, we can't say run over rise and, oh, it's the same thing, it's just reversed. It's like we need to do these, everybody the same way in order for it to make sense. Okay, so look very carefully. The way to not make mistakes on this is to realize, is your answer for your scale factor going to be smaller or bigger than 1 from the very beginning? So looking at these two, is the shape getting smaller or bigger? Yeah, we're going from A, B, C right here, which is small, and it's getting bigger. I know it's getting bigger because we always end with the primes, right? So A, B, C prime is bigger, so I know the k value is bigger than 1. So in case you happen to calculate this and you get something that's smaller than 1, you know you just kind of like you accidentally inverted the 2 numbers. Kind of like you switched the rise and the run and got run over rise instead. Okay. So let's just calculate. And the nice thing is, which side do we have to pick, though? Which side do we have to pick to calculate the scale factor? Yeah, look above. Which one gave us the right scale factor of 1/2? Yeah, it's all of them. Yeah. Yeah. So we're saying the point is that you guys you'll pick these things, whichever side you want to pick. You'll have different numbers, like we had, 3/6, 2/4, 1 point. You might have different work, but your scale factor has to be the same. Just know that when you guys are working on these separately and you're looking over or checking your answers and you're like, wait a minute, how come you did that number? I got this number. And at the very end, it should come out to be the same if we've done everything correct. Okay, it's one of those issues that sometimes people get a little worried if their work doesn't match somebody else exactly. So if you want to do the one that I'm going to do, go for it. But if you want to live slightly more dangerously, try one that I'm not doing. I'm going to do AC. I'm going to calculate AC and AC prime. So first I'll do AC prime. Now we're not going to use the centimeters because we actually have a grid, so we can count the rise, count the run, and use our distance formula. All right, so we're going to go up 1, 2, 3, 4, 5, 6, 7, 8. Got 8 squared, and then it's over 1, 2, 3, 4. There we go. So 8 squared plus 4 squared, that's going to be 64 plus 16. There we go. Which equals square root of 80. Root 80. And then let's do AC. Which is up 1, 2, 3, 4. 4 over 2. And here we have 16 plus 4, which is 20. Could you do, no, this way. Yeah, as long as you have a grid, you always want to use the distance formula. All right, and then let's calculate the ratio. Remember, the image, the ending part should be on top, so we want to do AC prime over AC which would be root 80 divided by root 20. And we need to get a decimal for that. So you might need a calculator, unless you know the square root rules and all that. And they're not too difficult, but just in case. Sometimes they're easy numbers like this, like 20 goes into 80, so it's a little bit easier. So since 20 goes into 80, what, 4 times? So root 20 goes into root 80, square root of 4 times. So it's basically the same calculation, just with a square root over it. Okay. And this time we can actually simplify square root of 4, which is 2. So we could say our scale factor here is 2. So technically, this outer triangle is exactly twice as big as its pre-image. Exactly. Okay. So that would be our answer right there. So a couple distance formulas, find the right ratio. And this does match with our original assumption that, well, this image is bigger, so my answer should be bigger than 1, right? And if we happen to mix up and we put the, inverted these or took the reciprocal of these, we got an answer of 1/2 instead. We should have red flags thinking that, wait a minute, that it's getting bigger, but my answer got smaller, something's wrong. So bigger image, number should be bigger than 1. It lines up. A little way to check your work. All right, so let's do one more. Same thing here. We can pick any side we want. So let's pick, let's see here. Do EA. Again, if you want to try a different one, go for it. It'll come out to be the same. There we go. So we have EA or AE prime. Oh, that's showing up. All right. Well, up looks like 1, 2, 3 over 1, 2, 3. So that's 3 squared plus 3 squared, which is 9 plus 9, which is square root of 18. All right, then repeat. Find out what EA is. EA. And it looks like it's up 1, 2 over 1, 2. So up 2 over 2, which is 4 plus 4 is 8. And then we'll do a ratio here. AE prime over AE. Yep, good. Which is root 18 over root 8. Okay, and what does that equal? So 8 doesn't go into 18 evenly, right? So at this point, you might want to have a calculator, right, that can give you that answer. Root 18 divided by root 8 is 1.5. Exactly. Okay. Well, if we did just 18 divided by 8, we get an answer of 2.25. So yeah, we do have to use a square root. But if we just took that answer, we do get that. So yeah, you can do a variety of ways, but you do need a calculator for some of these. So a little bit easier if you have the calculator, just plug it in as is, and we get 1.5. That's the scale factor. This pentagon is exactly 50% bigger, or 1.5 times the original. All right, so far so good. Not too bad, right? The only thing we really need to worry about geometrically is making sure our ratios are correctly placed. There we go. So let's do one more. Look over here, and we have this side right here. Let's do blue. Look at these two, AB. What do you notice about those two? Okay. What would the scale factor be for those? Yeah, so AB, we can tell just by looking at it, the K value will equal 1. Okay. What about the scale factor for another side? So what if I picked CB? It's not really important what the scale factor is. Is it the same as 1? No. So going back up here, right, these scale factors must be the same. So we know, because just by appearance real fast, we can tell, you know, the blue here and the orange here won't have the same scale factor. This is not a dilation. These are not going to be similar. Okay. So this is an example of, they call it a non-example, not a dilation, not a dilation, not, therefore, not similar. Okay. Not similar. And we're just kind of relying on some good judgment here. We didn't really do this mathematically. We just kind of said, well, look at it. You know, those are the same and those are different. We're not actually calculating it. We could find out what that K value is for the orange and then show it's not equal to K value for the blue. But this, for what we're doing right now, that's good enough. Okay? So 2 examples, 1 non-example of how to approach finding that scale factor and then determining if it is or not, is not. Technically, if we're going to be very picky, like we were above, you know, we showed all 3 sides for a 3-sided shape. All 3 sides have the same scale factor. And you'll notice for here, we just did one. But technically, we'd have to do this 2 more times and make sure they all came out to 2. If we had a pentagon, a 5-sided shape here, we'd have to do it 5 times and show they all came out to 1.5. We're not going to do that exhaustively. We're just going to assume this is similar, find the scale factor, and then might give you some pictures, kind of like we did with those quizzes lately. Just yes or no, is it a parallelogram or not, just by certain key information. Okay. So that's the big part. There's one little small part on the end, which is kind of interesting if you have ever taken photography or if you're in film, and it really helps you calculate perspective and then of where cameras should be or how far the video camera should be if you're doing a certain shot to get the right perspective. And that is finding the center of the dilation. Okay? And that's just basically a fixed point. Okay? And it's basically, if you had 2 shapes right in front of you, right? Let's say you're standing out here somewhere. You had 2 shapes right in front of you. How far would you have to be from them in order for these 2 triangles to look like they're exactly covering each other? They look like the exact same shape, even though they're not the same size and everything, where one covers the other one exactly, right? So what you do is you really just take 3, I think usually they do 4 points, but we're going to do 3 points here. And you just draw from B to B prime all the way through and just follow the line and see where they intersect. So we follow it there, then we do the same thing with A prime and A. And do the same thing with C and C prime. Okay. And then you'll get right there, center of dilation. That's right there. And I mentioned in my last class, I did have a student that was one of those students that said, I'm never going to use math and it's just never going to happen. And, I want to, go into construction and I just want to do that. They ended up getting with a construction union for Hollywood and building sets. And they actually had to calculate, well, where should, if you've ever seen movies being made, these cameras are on like rails and things like that so they can slide and get in certain shots. And they had to build a rail so they can get this certain perspective. They actually had to calculate how far it had to be to get that right perspective. And that basically, if you have a 3-dimensional set, they had to figure out, well, how far is it from here to here and draw that line and do this whole thing and get that camera placement perfect and build the rail for the camera so it went right in that path, like to have that perfect shot for the director. Because the director will just say, I want to have a perspective shot of this, and it's up to somebody else to calculate everything to build the set so they can get that actual shot. So it's kind of cool because one of those, in a million years, I'm never going to use this, and it doesn't happen, and math is just made up for us to be busy, and no one ever really uses it. And I mean, no one ever really uses it if they don't learn it, right? 100% of the people that don't learn math will never use it. It's the ones that do end up learning it. It's later on where you find out, like when somebody asks you, like, oh, you do some construction? Yes. Well, do you understand perspective? You know how to find like certain angles and certain, what's it called? Centers of, what are they called? Perspective. That's what it is. And mathematically say, yeah, I actually did do that a long time ago. I remember something like this. And they'll say, oh, great, you're hired. You can probably do this then. It's the person says, oh, no, I'm never good at math. I didn't know. I never learned it. And it's like, okay, we'll find somebody else. And it's just like that, plain and simple. So you never know. It's not that happens to everyone all the time, but it does happen. Okay, so we can get those two. So kind of a cool thing, especially if you're in photography or you're in videography. classes, camera placement is key. You can't just put it anywhere and think you're going to get the best shot by zooming. You generally don't want to zoom because that, decreases your resolution and all that good stuff. So, good place to use that. Okay, so you just have a few of those to do down below. You might want to actually start with these problems. They're the last two problems there. You can do them really fast and at least have the very end all tidied up and done. And then just go through and do the same thing. Remember, for each one of these, use your best judgment if it is or if it isn't similar, kind of like that last problem on the front. And if it does look like it's the same size or same shape but different size, go ahead and pick any of the three or four sides and just find that scale factor ratio. Okay. All right. And you got plenty of time, I think, to finish all of this in class if you just want to be done for the weekend. So